Hello physics students, this is Dr. Brinzy here. We're going to go through an example problem of a cannonball that's launched horizontally from a cannon, and it goes a certain range. I believe it says 95 meters right there. So it goes 95 meters and then lands in a pool, it looks like. And we're being asked what is the initial velocity of the cannonball coming out of this cannon. It looks like we're also given the height of the tower, which is 40 meters. Alright, so let's get started here. Let me erase that information. First thing that I want to do in any two-dimensional kinematics problem is identify what is given to me. Okay. And because X motion is independent of Y motion and vice versa, I actually like to make two different columns, one for the X motion and one for the Y motion. And I like to keep those separate. That helps me keep things organized. So let's figure out what's given to us in the X direction. Well, if we think back to our one-dimensional kinematics problems, there were 6 different variables we could identify. And the first ones were the initial and final position. The final position of this projectile is going to be, whoops, I started off with initial position, so let's do that. The initial X position, we'll call this 0 when it starts. So that's going to be 0, and then the final position of the projectile is going to be 95 meters. That was given to us in the problem. So I'm going to write xi equals 0 and x equals 95 meters. The second set of variables we identified when we were dealing with one-dimensional motion was the initial velocity and the final velocity. Since we have x and y directions, I am going to call the final velocity Vx, and the initial velocity in the x direction is going to be Vxi. So the final velocity Vx is going to be the velocity of the cannonball just before it hits the water. That velocity will have an x component, and that x component vector looks like this. Likewise, up here at the top, it starts off with an initial velocity, and its x component is going to be Vxi. Since that is what we're trying to figure out how fast the ball comes out of the cannon. That is actually what my unknown is. That's the unknown I want to find out, so I'll put a question mark next to that. We learned that there is no acceleration in the horizontal direction because the only thing acting on this ball is gravity, and gravity only works in the y direction, so I can say that my acceleration in the x direction is equal to 0. Now in one-dimensional motion there was another variable, time, that we put in along with these other 5, but I actually want to save that for later, because now time doesn't apply just to the x direction, but it also applies to the y direction as well. Now let's go to the y direction, and let's define what its final position and initial position are. So this is the final y position of the projectile. This is the initial y position of the projectile. The final y position is 0 because it is landing on the ground, and we're defining y equals 0 is the ground. Its initial position, way up here, when it's first shot out of the cannon, is positive 40 meters. So y is 0 and yi is positive 40 meters. We have velocity in the y direction and initial velocity in the y direction. When the ball is shot out of the cannon, it doesn't have a vertical component to its velocity, so I can say that Vyi is equal to 0, and I'm going to go ahead and fill in that 0 down here. However, when it lands, it will have a component in the y direction. So you could imagine a y component of its velocity, and that vector would look like that just before it hits the water. And the reason that this one is growing is due to gravity, right? Gravity is an acceleration, or there's an acceleration due to gravity, rather. And because of that, my velocity in the y direction actually grows as this cannonball goes further and further along in its trajectory. Okay, like I said before, oops, I'm sorry, I forgot about acceleration. The acceleration in the y direction is due to gravity, so the a sub y is equal to negative 9.8 meters per second squared. That will always be true for all projectiles. Now, to talk about time. Time is shared between both directions, so what I like to do in my little organizer here is I like to actually create a little space down here where time can be shared between the two of them. So let's do that. Let's shorten that line a little bit, and then to put a t equals, I'm not given the time of flight of the projectile. I'm not given the time that it takes to hit the ground, so I have to leave that blank. Now, in your notes, I want you to keep this. Don't erase anything. But as I go on to my next slide, I actually have to transfer some of this stuff. So here we go. This is the same stuff we wrote on the previous slide. So you don't need to do anything. Don't need to write anything new from this stuff. There we go. Okay, now I'm fully caught up. So on the last slide, we figured out all the givens. Now on this slide, we want to figure out which equations we can use. There should be an S on the back of that. There we go. There it is. There we go. Okay, good. So what equations do we have available to us? Well, they're the same equations that we used in one-dimensional motion. We have the displacement equation. So let's write the displacement equation for the x direction. So we have x equals xi plus vxit plus 1/2 axt squared. Now we can simplify this a little bit because this term, because acceleration is 0 in the x direction, this term is always going to equal 0. So there's no real reason for us to have it on there. So you can take a little shortcut and just write this for the horizontal direction. There's no acceleration in the horizontal direction, so you can just write these first two terms out and leave the last term off for this particular direction. It's not true in y, but it's true in x. Now there were two other equations that we could write. You may or may not remember what they are. But what happens is that if you have no acceleration, it turns out that those two equations, all they tell you is that your velocity is going to remain constant. Your final velocity in the x direction is going to equal your initial velocity in the x direction. So whatever this number is, it will also be that number right there, and vice versa. Okay, now let's write down the same kinematic equations in the y direction. There's our kinematic equation for displacement, the one that we just did, except now we're replacing x with y's. The same equation, just a different direction. Then we have two more equations. We have Vy equals Vyi plus Ayt. So final velocity equals initial velocity plus acceleration times time. And then you have the v squared equation. This is velocity squared equals initial velocity squared plus 2 times acceleration times the change in position or displacement in the y direction. Okay, so now that we have all of the equations written down that we can use, let's go ahead and figure out which equations will actually be useful to us in this particular problem. Now, when we did problems in one dimension, or 1D kinematics, you had all of these unknowns, and you had all these equations. You had three different equations, pretty similar to what we have over here in the y direction. So unknowns or givens, and you had equations. And then we asked ourselves, okay, which of these unknowns do I not know and am I not interested in? And that is going to be a variable I want to avoid. We have two directions this time, so it gets a little bit more complicated, but not much more complicated. First of all, we're going to start off with the side where we want to find something. In this case, we want to find the initial velocity in the x direction of this cannonball, so this is where I want to start. So I want to start on the x side, and I have I want an equation that solves for this that doesn't involve Vx. Well, in the x direction, we only have one equation that will be terribly useful to us, and that's this one right here. So like I said, I want to avoid this variable, which means this equation really doesn't help me that much. And I'm stuck with this one. So let's go ahead and fill in. Oops, sorry about that. One other thing, in the y direction, we also want to avoid this variable, since we don't know it and we're not interested in it right now. So let's cross out all of the equations that will avoid Vy, or that have Vy in them, so that we can avoid those equations. So let's cross out the ones with Vy. That means we have to cross out those two right there, and it looks like in the y direction we're just left with this equation here, and we're left with that equation there. So those are the two equations that it looks like we can work with in this particular problem. So we've taken the 5 equations that we worked with and we've cut them down to 2 equations we can work with. Okay. Now, you don't have to actually erase these on your paper, but I have to erase them on my board so that we have a little bit more room. So I'm going to erase this equation. Basically, these equations we crossed out, I'm going to go ahead and erase those. And we're going to go ahead and solve for the initial velocity in the x direction, which is what we want to find out. So let's erase those. And let's go ahead and start plugging numbers into this equation right here. So I have 95 is equal to 0 plus Vxi, that's what I want to find out, times t. Well, it looks like I'm stuck here because I don't know that, that's what I want to find out, but I also don't know time. I don't know how long it takes for this object to land on the ground. What do I do about that? I mean, it's apparent that I'm stuck here. But let's not forget that we have another equation over here, and we could possibly use this one to help us solve for time. So let's see if we can use this one to solve for time, and then plug that into here. So let's turn our attention to the y side of things, the vertical side, and let's plug in what we know on the y side of the bar here, and it looks like I have 0. Whoa, getting a little ahead of myself there. Sorry about that. There we go. Let's back that up. Okay, so I have 0 equals 40 plus 0 times t plus 1/2 times negative 9.8 times t squared. Now I'm going to simplify that, and I'm going to get 0 equals 40 minus 4.9 t squared. Well, that's an equation that we can solve for t. The first thing we got to do is get t squared by itself, and when we do that, we're going to end up with something like t squared equals 4.01. I think that's right, or it's close to it. And then we take the square root, and when we take the square root, we're going to get plus or minus 2.01 seconds. But the negative root doesn't make too much sense to us because we're not counting negative time. So it's just going to be positive 2.01 seconds. Okay, I was able to solve for time. So let's plug that into the x equation now. And when I do that and solve for the initial velocity in the x direction, I find that we have 47.5 meters per second. So that's how fast the ball is being shot out of the cannon horizontally, the cannonball. Okay, so that's an example of a two-dimensional kinematics problem that you're going to have to solve. Sometimes it involves doing two different steps, like when we got stuck here, we had to actually come over here. That does happen from time to time, so that's just something that we have to get used to in advanced physics. It's harder, but we also have more math skills and we can work on solving more complex problems like this using our math and using some thinking power here. All right, we're going to work on this more in class tomorrow. I look forward to seeing you then. Bye.